Welcome to The Explainer. Today, we're going on this really fascinating journey. We're going to start deep inside the mind of an AI, then move through the world of super complex code, and we're going to end up with a physical, interactive device you can actually hold in your hand. Exactly. We're connecting the dots between some huge breakthroughs in AI efficiency, automated coding, and even 3D fabrication. We're going to look at research on methods like EvolKV and AutoVeriFix and see how they lead to these incredible new techniques like projection. It's really a complete pipeline from an idea to a real-world object. Okay, let's dive in. So we're going to start at the very core of the AI itself. Because, before we can ask an AI to build things for us, we have to make sure it's thinking as efficiently as possible. Well, it really just comes down to memory. As we feed AI models longer and more complex information, I'm talking entire books or huge code bases, their memory usage just explodes. And this is a massive problem because it makes processing all of that information prohibitively slow and, you guessed it, expensive.
Right, and the key to this whole thing is something called the KV cache. Honestly, the easiest way to think of it is like the AI's scratchpad. When it's processing information, it jots down important notes in this KV cache so it doesn't have to recalculate everything from scratch every single time. It's absolutely essential for speed, but it's also what fills up so darn quickly.
So the big question is, how do you manage that scratchpad? For a long time, the approach was based on these really rigid static rules. Things like always keep the first few notes and the most recent notes. But a recent paper introduces a method called EvolKV that just throws that old thinking right out the window. Instead, it uses evolutionary algorithms to let the AI adaptively figure out the best memory strategy for whatever task it's doing.
And this is where it gets really, really interesting. The evolutionary search found that treating all the AI's layers the same is actually super inefficient. The best strategy is a completely non-uniform, custom allocation of memory. Some layers need a ton of scratchpad space, while others need very little. It's a pattern that, honestly, no human would have likely come up with on their own.
And the results? They're really impressive. On a complex mass benchmark, EvolKV achieved 95.7% of the full model's performance while using just a tiny fraction of the memory. This just goes to show that an adaptive approach can make AI drastically more efficient without a major drop in performance.
Okay, so now that we have a more efficient AI, what can we actually do with it? Well, let's move on to our next section and see how this all builds into making AI an indispensable partner for writing and fixing code.
One really powerful application is code completion. Now, to improve this, one team of researchers proposed a hybrid model that's kind of like having two specialists working together. First, a model called CodeBERT analyzes the existing code to deeply understand the context. Then it hands that understanding off to a powerful generator, in this case GPT 3.5, which then writes the new code. You're basically combining a great reader with a great writer.
And you can see on this slide just how effective that pairing is. Looking at the F1 score, which is a key measure of accuracy, the hybrid model hits 0.91. I mean, that's a real jump over what either model could do by itself. It's a perfect example of the whole being greater than the sum of its parts.
Okay, so this works for general code. But what about something much more high stakes? Can AI really handle code where a single mistake could cost millions, like, say, designing a computer chip?
That's exactly where the challenge is. In hardware design, a single functional error in the code, which is known as Verilog, can lead to millions of dollars in wasted manufacturing costs. The stakes are just incredibly high.
So to tackle this, researchers developed this framework they call AutoVeriFix. And I just love their analogy for it. It's like a teacher and a student. First, they have a large language model generate a Python model of the hardware's intended behavior. This Python model is the teacher, and it's almost always correct. Then, this teacher model is used to create a whole bunch of tests that automatically find and fix errors in the much trickier Verilog code, which is the student.
And this chart just shows the massive impact of that teacher-student approach. On its own, GPT-4 got about 59% functional correctness. Not great. But with the AutoVeriFix framework, that score jumped to over 83%. In academic terms, that's the difference between a failing grade and a solid B. And in the world of hardware, that's a total game changer.
Okay, wow. So we've made the AI more efficient, and we've used it to write and debug these incredibly complex digital blueprints. Now for the final leap, turning that digital information into a physical object that you can actually use, right off the printer.
This brings us to the core idea from a paper called Printed Circuits.
The goal here isn't just to 3D print a plastic case that you have to assemble later. No, we're talking about fabricating a complete, self-contained, interactive object, like this Toon Shroom musical instrument or the Snail Sense plant monitor, directly from the 3D printer.
And the magic behind this is a new technique they came up with called prinjection. The process is just brilliant in its simplicity. During the prints, the machine pauses. You drop in a standard circuit board, and then the printer uses its conductive filament nozzle to literally inject molten conductive plastic directly into the little holes on the board where you would normally have to solder wires.
Yeah, it's this very precise, automated sequence. The printer head moves over the hole, it lowers the nozzle right onto the surface, injects just the right amount of conductive filament to fill that hole, it wipes the nozzle to prevent any stringing, and then it lifts up to move to the next connection point. This creates both the electrical and the mechanical connections all automatically.
This visual really shows you everything you need to know. On the left, without prinjection, the conductive trace is just kind of sitting on the surface. It's a weak connection. It could easily peel off. But on the right, with prinjection, the filament has totally fused into the hole, creating a robust, reliable anchor for both the electrical signal and the physical structure. The difference in quality is just night and day.
The researchers summarized their goal perfectly. They said they are using traditional electronics as material to 3D print self-contained interactive objects. This means the circuit board isn't something you add later, it actually becomes part of the raw material that the printer uses to create the final product. It's a fundamental shift in thinking.
And this brings us to our final section, where we get to tie everything together. We've seen 4 pretty distinct innovations, but they're all pointing toward a single, revolutionary future. Exactly. Let's just quickly trace the path we've followed. First, we started at the core, optimizing the AI's memory with techniques like EvolKV to make it smarter and way more efficient. Then, we used that smarter AI to automate the creation of complex digital blueprints with frameworks like AutoVeriFix. And finally, we saw how to directly fabricate those blueprints into physical objects using prinjection. It's this seamless progression from an optimized thought process all the way to a finished device.
Which leaves us with a pretty fascinating final question. We've just walked through a pipeline where our intelligent digital tools are becoming capable of designing and building our physical ones, completely automatically. It really makes you wonder, when that process becomes truly seamless, what will we even be able to imagine and create next?